Hello, my name is Hunter Gibson, and this is Project 1.5, the counting circuit. First off, the main theory behind the circuit. Project 1.5 serves as a starting point into the functionality of digital devices, focusing on oscillation, counting, and display capabilities. Using several stages or subcircuits, each with a specific role, the system embodies the core principles of digital electronics. At the heart of the circuit lies the analog input stage, where external signals are received to initiate the counting process. These signals serve as triggers for the subsequent stages, setting the foundation for the entire circuit. This circuit uses a momentary PBNO, which is a type of switch that is normally open, meaning it doesn't connect electricity until pressed. In the pull-up resistor configuration like we're using, the resistor connects the PBNO to power. In a pull-down resistor configuration, the resistor connects the PBNO to the ground. Next, the system transitions into the NAND gate oscillator using the 4011 chip. It is responsible for generating a clock signal, which is essential for counting. The clock signal consists of pulses characterized by both duration and frequency, serving as the rhythmic heartbeat of the circuit. This clock signal is a periodic waveform with a specific frequency which is used to synchronize the operation of the circuits. It provides a timing reference for a lot of operations within a digital system, ensuring that different parts of the system operate together. In the context of the counting circuit, the signal generated by the NAND gate oscillator using the 4011 chip determines the speed at which the counting circuit increments or decrements, depending on if the circuit is counting up or down. These clock pulses then go to drive the decade counter using the 4017 chip to incrementally count. The decade counter plays a pivotal role in tracking and storing these counts, paving the way for further processing. A decade counter circuit is a digital circuit that can count from 0 to 9 and displays the count using LED segments. We use an LED bar graph which shows the count's progression visually. Next, the decimal counting binary up-down counter, which uses a 4510 chip, comes into play, offering counting capabilities in both upward and downward directions. This counter enhances the functionality of the circuit by allowing different counting scenarios. The 4510 chip receives BCD data via input pins, where it is set to the initial count value and the sequence starting point. The chip internally processes the input and increases the count from the NGO, using logic circuits to read and advance the count in BCD format. The chip's output, which are shown on pins Q0, Q1, Q2, and 3, show the binary coded decimal count, with each pin correlating to a distinct bit and making the final count number. Following the counting process, the binary counting decimal encoder, using the 4511 chip, translates the binary count into a format suitable for display on a 7-segment display. This stage ensures that the count is presented in a clear and readable manner for users to interpret easily. Finally, culminating in output, the 7-segment display visually represents the pulse count, providing a very user-friendly interface. To bring the system together, a dedicated counting circuit PCB is used to integrate all components. This PCB acts as a central hub that facilitates communication among different stages. By exploring each stage within this counting circuit, we are able to gain valuable insights into the underlying principles of digital systems and their applications in the real world. Thank you.